Welcome back to the module on one-sample hypothesis tests. I'm Ellen Gordon. In this module, you will learn how to conduct a one-sample z-test. I will introduce this test with a business problem. Snowville Creamery is a local dairy company. It is important for Snowville Creamers to verify that their milk cartons are being filled at the advertised weight, which is a half gallon or 1.89 liters. They do not want a problem of underfilling the cartons. This would mean that their customers are being shortchanged, which is a form of false advertising. They also don't want a problem of overfilling the cartons, which would be an unnecessary cost to the company. There is some variation from carton to carton because the filling machinery is not perfectly precise. That is, not every single carton weighs exactly 1.89 liters of milk. They know that the standard deviation is 0.08 liters. This means, on average, a carton is about 0.08 liters away from 1.89. The company needs to periodically test the cartons to confirm that the average weight of all cartons is 1.89 liters. That is, they want their population mean to equal 1.89. However, it's impractical to weigh every single carton in order to assess or obtain a population mean. Instead, they should collect a sample and use that data to make a conclusion about what the population average weight is. However, we know a sample mean is probably going to differ from the population mean. For example, the population average weight could be 1.89 liters, but we could get a sample mean of 1.9. So, how big of a difference does there need to be in order to suggest that the cartons are being over or underfilled? And hypothesis testing can answer that question for us, specifically a one-sample z-test. Here are the steps of hypothesis testing. The steps are the same for every single hypothesis test. However, the method for completing the step differs from test to test. For example, in step 6, which is computing the test statistic, each test statistic has a different formula. Step 1 is choosing the appropriate statistical test. The first thing you do when you want to test a hypothesis is to determine the appropriate statistical test. We are going to conduct a one-sample z-test. You conduct a one-sample z-test when you're interested in comparing two group means. For one group, you have sample data. This is considered to be the group of interest. For the other group, you know the population mean. The population mean is either known or claimed or desired. We also know the population standard deviation. If you refer to your prep assignment, you can see over to the right, there's the research description. I have already introduced you to the problem. Here it says the quality control department periodically takes a sample of bottles to measure their fill and verify that the filling machinery is working properly. They randomly select 25 bottles from the production line, and the data is presented in this worksheet. Conduct the appropriate hypothesis test with a significance level of 0.05 to determine if the current mean fill of the bottles differs from the advertised level. So we're comparing two means. We're comparing the current mean fill to the advertised average. And the advertised average is a population mean, it's a desired population mean, and then for the current mean fill, we have 25 bottles, so that's a sample. When you are trying to determine the appropriate statistical test, I think a lot of times it's beneficial to complete this descriptive statistics table that will allow you to see what kind of data you're working with, and it will help determine the appropriate statistical test. So we have advertised average. The advertised average is 1.89 liters, so I'm going to type that in. And then advertised standard deviation, that is 0.08. So again, the filling machinery is not exactly precise and has a standard deviation of 0.08. So we have 0.08. And then advertised sample size. This is a population mean. It's a desired population mean, so it's not a sample and it does not have a sample size. So for the current average, we can compute that using the Excel function. The current standard deviation, we can also use the Excel function. Remember, for standard deviation, there's .p and .s, depending on whether you're working with sample or population data. We're going to use .s because we have sample data. We also want to determine the sample size. We know from the research description it's 25, but we can use the count function to verify that's how many data points we have. All right, you can see that we have two groups current fill versus the advertised fill. The advertised fill is a population mean, it's not a sample. We also have a standard deviation, and the current average fill is based on a sample of bottles. So we have one sample, we're comparing it to a population mean, and we know the population standard deviation. So that means that the appropriate statistical test would be a one sample z-test. The next step is to identify the case, whether the test is one or two-tailed. You should remember from the last video that this is based on the research hypothesis, or what you would predict or expect the results to be. In this class, the research hypothesis will be provided to you in the research description. As a reminder, a two-tailed test is when you predict that the two means or two groups will be different. A one-tailed left is when the group of interest is predicted to be less than the population mean, and a one-tailed right is when the group of interest is predicted to be greater than the population mean. If you return to your prep file, we can read the research description and determine the case. So you can see here it says conduct the appropriate hypothesis test with a significance level of 0.05 to determine if the current mean fill of all bottles differs from the advertised level. So we're just looking to see if the current mean fill is different from the advertised fill. There's nothing in this research description where we think that they're underfilling the bottles or overfilling the bottles. We just want to see if it's different from the advertised level. So that would make it a two-tailed test. The third step is the hypotheses. Again, these were covered in the previous video. As a reminder, all tests contain two hypotheses, the null and the alternative. The null hypothesis is the hypothesis of no significant difference, and the alternative hypothesis is the research hypothesis. In our problem, the null hypothesis would be the current weight of the cartons is not significantly different from the advertised average of 1.89 liters. The alternative hypothesis would be that the current weight of the cartons is different than the advertised weight of 1.89 liters. If you look at this table, you can see the hypotheses and symbols. Again, these were covered in the previous video. We are conducting a two-tailed test, so if you refer to this area of the table, you can see what our hypotheses should be. If you return to the prep file, again, the null hypothesis is that there's no significant difference, so the two means are the same or they're equal, and the alternative is that there's a difference, so the means would not be equal. Step 4 is to set alpha. Alpha is referred to as the level of significance. It can also be denoted with the Greek symbol alpha. If you look here on the PowerPoint, this is the Greek symbol alpha. So the results of the statistical test will tell us to either reject or fail to reject the null hypothesis. Alpha is an objective rule for when we will reject or when we will fail to reject the null hypothesis. Here is the distribution under the null hypothesis. Again, our null hypothesis states that there is not a significant difference between the current fill and the advertised fill of 1.89. So they have the same distribution with a mean of 1.89. Again, we know a sample mean is going to differ a little bit from the population mean. And it turns out that sample means are normally distributed. So there's a good chance that we'll get a sample mean that's a little bit above or below the population mean of 1.89. For example, if we got a sample mean that fell here on the distribution, that would be expected, or if we got a sample mean that was a little bit less than 1.89 and fell right here on the distribution, that would be expected as well. However, it would be very unlikely that we would get a sample mean that would be all the way out here on the tail. So if we got a sample mean that fell out here, that would suggest that the current fill is not under the distribution with a mean of 1.89. It belongs to another distribution, and the population mean is greater than 1.89. On the other hand, if we got a sample mean that was much below 1.89 and fell all the way out here on the tail, that would suggest that the current fill does not belong to this distribution. The current fill is a different distribution, and it has a population mean that's less than 1.89. We typically set alpha at 5% or 1%. In the real world, the analyst picks alpha, and typically people go with 5%. However, in this class, alpha will be provided to you, and it will be provided in the research description. If you return to your prep file, you can see the last sentence is conduct the appropriate hypothesis test with a significance level of 0.05. Again, another term for alpha is significance level, so our alpha is 0.05 or 5%. So we can indicate that it's 5%. So our alpha is 5%. So basically what that means is if our sample mean is in the top or bottom 2.5%, we will reject the null that the population mean is 1.89. It's very unlikely we would get a mean like this if the population mean is really 1.89. So if our sample mean falls in the shaded areas, we will reject the null hypothesis that the current fill is 1.89 and we'll conclude that it's different. These shaded areas are referred to as the rejection region. If the sample mean falls in the middle area, then we will fail to reject the null and conclude that the population mean, the current fill, is 1.89. The middle area is referred to as the fail to reject region. Step 5 is to compute the critical values. Critical values are the z-scores associated with alpha. In our example, we wanted to determine the z-scores that are associated with the bottom and top 2.5%. If you remember, we use the I and v functions to determine the z-scores given the percentage. Here are the Excel functions. Note that there's different functions depending on whether it's a one-tailed left, one-tailed right, or two-tailed. When you conduct a two-tailed test, you have two critical values, a lower and an upper. They will be the same number, but the lower will be negative and the upper will be positive. The Excel function for the lower limit, the lower critical value, is norm.s.inv. And then we take our alpha and we divide it by 2. For the upper limit, it's norm.s.inv, and we do 1 minus our alpha divided by 2. And again, you can see that the values are the same. It's just that the lower is negative and the upper is positive. Here's a visual depiction of our critical values. Again, we had an alpha of 5%. We divided it by 2 because we're conducting a two-tailed test. So we have 2.5% in both tails. We have the upper 2.5% and the bottom 2.5%. And what we did was we found the z-scores that are associated with the top and bottom 2.5%, and those are called our critical values. The next step is to compute the test statistic. This is the z-score for our sample mean. First, we have to compute the descriptive statistics, which we already did. Remember, the population information will be provided in the research description, and the sample statistics will be computed using Excel functions. We can then compute the z-statistic. It is the sample mean minus the population mean divided by the population standard deviation divided by the square root of the sample size. So again, in order to compute the test statistic, you have to complete the descriptive statistics. The population information comes from the research description, and the sample statistics were computed using Excel functions. The formula for the test statistic is the sample mean minus the population mean divided by the population standard deviation divided by the square root of the sample size. And our test statistic is 2.5. Again, our test statistic is a z-score for our sample mean. The star denotes where it would fall on the standard normal distribution. Step 7 is to compute the p-value. The p-value is the probability or the percentage associated with our z-statistic. You may remember from the previous module that we used the dist function to determine the percentage. Here are the different functions depending on what type of test you're working with, whether it's two-tailed, one-tailed left, or one-tailed right. Now we can compute the p-value. The formula is 2 times the norm.s.dist function. And what we do is we take -1 times the absolute value of our test statistic. And then for cumulative, we write true. We can formulate our p-value as a percentage. Here's a visual depiction of the p-value. Again, the star represents our test statistic. The p-value is the percentage in the area to the right of the z-statistic or test statistic. We multiplied our p-value by 2, so the true percentage is really half of 1.24%. Now we need to determine if we should reject or fail to reject the null hypothesis. There are 2 approaches to make that decision, the critical value approach and the p-value approach. These 2 approaches will always give you the same result, that is, they'll always be in agreement. For the critical value approach, we will compare our z-statistic to the critical values. If the z-statistic falls in the rejection region, we will reject the null hypothesis. Again, the rejection region is the yellow shaded areas on the distribution. If the z-statistic falls in the middle, the fail to reject region, we will fail to reject or accept the null hypothesis. In our example, you can see that our z-statistic of 2.5 is farther out on the tail in comparison to the critical value of 1.96. It falls in the rejection region. Therefore, we will reject the null hypothesis. Here are the written guidelines of the critical value approach, depending on the type of test. Again, we are conducting a two-tailed test, and our test statistic was positive. It was 2.5. And our test statistic of 2.5 was greater than the upper critical value of 1.96. Thus, we will reject the null hypothesis. We can also determine if we should reject or fail to reject with the p-value approach. If the p-value is less than alpha, we reject. If the p-value is greater than alpha, we will fail to reject. Many times people will use the saying, if the p is low, the null must go, to make it a little bit easier to remember the p-value approach. Here's the visual depiction of the p-value approach. You can see that the p-value, the area to the right of our test statistic, is less than or smaller than alpha, which is the area to the right of our critical value. If you remember, with a two-tailed test, what we did was we split alpha into two tails, so we really have 2.5% in each tail. However, remember, for our function for the p-value, we multiplied it by 2. So we really can just compare the p-value that Excel gives us to the alpha of 5%. In other words, when it's a two-tailed test, you don't really need to divide alpha into 2 because we're multiplying our p-value by 2. If this is confusing to you, just know that when you do the p-value approach, no matter what kind of test it is, all you have to do is compare the p-value that Excel gives you to the alpha that's provided in the project description. If your p-value is less than alpha, you will reject the null. If your p-value is larger than alpha, then you will fail to reject. So according to the p-value approach, we are going to reject the null hypothesis. Our p-value of 1.24 is less than our alpha of 5%. And also according to the critical value approach, our test statistic fell in that critical region, so we are going to reject the null hypothesis. Finally, we need to write our conclusion. If you fail to reject the null, you would simply repeat the null hypothesis that there's not a significant difference. However, when you reject the null, which was the case in this example, your conclusion is the alternative hypothesis. In this PowerPoint, I have a template for how to write the conclusion depending on the different types of tests. We conducted a two-tailed test. So that means that we did find a significant difference between the group of interest, which is the current fill, and the population mean, which was the advertised fill of 1.89. So again, we found that there is a significant difference between the current fill and the advertised fill of 1.89. So that is what the test indicated. However, if you conducted a test like this in the real world, if you were actually working for quality control and you found that there's a difference between the current fill and the advertised fill, and you gave this report to your boss would probably ask, well, what's going on? Are we underfilling the bottles or are we overfilling the bottles? So what you would want to do is you would want to include that in your conclusion. So what we can do to figure out if they're overfilling or underfilling is we can look at our means. The current average had a sample mean of 1.93. The advertised average is 1.89. We found a difference, and the current average is greater. So it looks like they are overfilling the bottles. So what we can do is we can write the data suggests that the cartons are being overfilled. When you reject the null hypothesis, your conclusion is the alternative hypothesis. So for a two-tailed test, really the only conclusion that we can draw is that there's a significant difference. However, in practice, typically what people do is they expand on the conclusion and they talk about the direction of the difference. So they talk about which group is greater, which group's mean was less. However, technically what you're supposed to do is when you find a significant difference for a two-tailed test is you're supposed to conduct a follow-up study to confirm the results. So in our case, what we would want to do is we would want to collect data from more cartons. We would want to conduct a one-tailed right, and we would hypothesize that we think that they're overfilling the cartons, and then we would see if the data confirmed that hypothesis. So to summarize, this test analyzed the null hypothesis, which is the current fill is an average of 1.89 liters. We found that our sample mean was all the way out here on the distribution. There was less than a 5% chance we would get that sample mean if the population mean was really 1.89. So we are rejecting the idea that the current fill is 1.89 liters. And so we are then inferring that the current mean is greater than 1.89 liters.